force versus time. So you got like a graph. Here's the force, like that. So this is time. This is force. And the question is, using graphical methods, count squares to estimate the total impulse given to the ball. All right. And then estimate the velocity of the ball after being struck, assuming the ball is initially at rest. So the mass of the ball, this is a force on ball with mass equal to 0.06 kilograms, which is the book's preferred mass for a tennis ball, apparently. All right? That's good. Okay, so what on earth does impulse have to do with average force? Well, let me just share a little bit of calculus with you briefly. So F is the change in momentum over the change in time, right? We've talked about that already. That says that the change in momentum is equal to the force times the change in time. All right? And so if you want to calculate the net change in momentum, this implies by calculus that the net change in momentum is equal to the integral of F times dt over the interval. Let's just say integral. But the integral, we learn in calculus, is what that does is it calculates the area under the graph of F. All right? So that's why the area under the graph of F gives you the impulse. Now, I mean, whether or not you know calculus, this is nice to know because, you know, if you have a graph of a force that is applying to something you're doing, then if you can find the area under the graph, then that gives you a sense of how much momentum that force imparts, in this case, the ball. So all you have to do there is basically look at the graph which is given, count the squares, and that will tell you the area. That area is the impulse. Okay? And then there's some units given on the graph, like, let's see here. This scale is like 0.1 seconds. This is like 0.05 seconds. And I think this is something like 100 newtons. Let's just make up our own numbers just for the sake of discussion, okay? If that's 100, that's 200, and this is about, you know, 0.1 seconds. What's an easy way to kind of estimate the area? Think about this. If you could find a dividing line where half of the area was above and half of the area below, wouldn't that tell you something about the area? Maybe? I don't know if that, let's see here, maybe a little lower, right? I think if I do that, then I think the area down here, I don't know if that helps or not. I don't know. How do you estimate area? You could actually just count boxes in the problem in the book, right? I'm trying to make this too complicated. Let me just estimate. How would you be able to divide it from that side instead of vertically? Oh, I don't know what I'm doing. I mean, I'm just. I can do it with calculus. I haven't thought about how to calculate areas without calculus too much, honestly, guys. Because I'm so used to using calculus, it's hard for me not to. It seems to me like, roughly speaking, this is about as big as this box. So for I would estimate the area on my board problem is, I don't know, 0.03 seconds times 200 newtons, something like that. I need to get a number. I need to find a number here to finish the problem for you guys without counting the boxes on that. So what is 200 newtons times 0.3 seconds? What's the impulse there? Oh. Yeah, 6. It's kind of anticlimactic. 6 kilogram meters per second. So if that's the case, what's the speed of the ball after it's hit by this thing that has this particular force profile. Remember, the change in momentum over the, well, the change in momentum is equal to 6 kilogram meters per second, right? That's the impulse. The net change of momentum is that. And that is 0.06 kilograms times the velocity minus the initial velocity. What's the initial momentum? The ball's at rest, right? So the final momentum minus the initial momentum is the final momentum. So all I have to do is take 6 and divide by. Ooh, wow, it's kind of moving. So I get VF of 100 meters per second. Yowzers. You do not want to get hit by that tennis ball. I'll tell you that right now. So that's how to do 23. You need to find the area under the graph and then interpret the area as the impulse. That's the. You don't need calculus to do that. Calculus gives us an interpretation, but what you do with it is up to you for that. So anyway, we will continue on. Next time I'm going to focus more on the issue of an elastic versus an inelastic collision. And so I hope you'll find that to be a more interesting discussion than this one. Hopefully we'll have lights. We'll see.